party, shall we? And by party, I mean recording and class. So yes, as we've been discussing, we're in the home stretch, the downhill slide, whatever your metaphor is. 3 weeks of class left after this one. So I wanted to make sure that everyone was aware of the work that is still in front of you. We have another formative assessment open that is due Monday. You should be able to answer all of that. I am very close to having finished your next homework, which is going to be based on what we're talking about now, and I've already preemptively moved that to the Wednesday of the following week. That way we'll make sure that everyone has enough time to finish it. One more formative assessment, and then instead of a final exam, just another homework. And I think it's going to be due like maybe 17, 18 points or something like that, enough to where no one can skip it. I've learned that lesson before. Like, don't make it worth 10 points, because then there's people that are like, I got enough points, I'm done. So you will not be able to get your B or whatever your minimum acceptable grade is without finishing all the homeworks. But it's just a regular homework, so I'll let you know when it's available, and if you can get it done before finals week, then you can check the box for this class and be done. And in case anyone is looking forward to using finals week to catch up on work that is still outstanding, I wanted to point out that we are not meeting as a class during finals week because it's finals week, but I am using the same amount of time I would normally spend being in front of my classes to hold office hours. So Tuesday and Thursday on finals week, I will be in Zoom office hours from 12:30 to 4:30. That way, if anybody needs some extra help getting finished with everything, I will be available. So I will let you know when your next homework is ready. Formative assessment is the next thing to do until then. Okay. Any scheduling logistics questions? No, we're good to go with that? All right, I'm going to shut this down. So then we have today a few slides left in Lecture 4 and then a new example that I put together that is meant to be really just a review. So trying to give you more exposure to data and strategy in terms of how you would go about building models to answer research questions. So I was on the fence as to which I wanted to do first. Does anyone have a preference? Like 4 more slides versus example?
4 more slides.
4 more slides? Because then you can have that feeling of accomplishing something, like shutting Lecture 4 down. Let's do that then. So we've been talking about what happens when multiple predictors representing different concepts are combined into the same model. The short answer is that the relationships that the slopes are capturing are unique relationships. So what is the effect of predictor X after controlling for predictor Z? What is the effect of predictor Z after controlling for predictor X, and that kind of thing. And in that situation, it is possible that you may see some strange things. So the last few slides are about the strange things that you may see in your regression models. Such as, slide 31 here, suppression. In general, when we are talking about the change in a slope, when it describes a bivariate relationship to when it describes a unique relationship, it usually gets smaller. Because to the extent that predictors have something in common, that common variance is not counted in each of their slopes. So if the part that's overlapped, that in terms of the prediction, no predictor gets individual credit for. So most of the time, unique relationships are going to be smaller than bivariate. However, that is not always going to be the case. So there is a name for when the relationship turns out to be bigger after you control for something, and the term of that is called suppression. And these are mathematical considerations as to when this will happen. The one that I've seen most commonly is when you have predictors that are negatively related to each other. So a negative correlation means as x1 goes up, x2 goes down. And when that happens, you can see some funky things when you put them together in the same model. So for example, I stole this example from the Cohen, Aiken, and West regression book. They reported a story in which they were trying to predict an outcome of sales success from assertiveness and record-keeping diligence. Well, you can imagine those things do not tend to go hand in hand. People who are more diligent and detail-focused at record keeping may not be the most assertive folks, but both of these would be important to being a successful salesperson. So they reported the bivariate correlations between these variables. So Y, sales success, is correlated with assertiveness 0.4. It's only correlated with record-keeping diligence 0.13. Then there's a negative correlation between the two predictors. Well, when they get put together in the same model, they reported standardized slopes that are actually larger than the bivariate slopes. So this can happen. It doesn't mean that you did something wrong, but this is one of the reasons why you can't necessarily anticipate from just looking at correlation patterns what's going to happen when you put multiple predictors together into the same analysis. Here are some other things that can happen. This is actually SPSS output. I borrowed this example from the person who taught me regression, Cal Garvin at the University of Nebraska. And I also borrowed this to make a point that, yes, SPSS can do the models that we're talking about in this class. So if you have an advisor who has pledged allegiance to SPSS, no worries. Your textbook has SPSS code to do all of these things. The reason that I don't favor SPSS is because it tops out at a lower place than the other programs do. It does fewer advanced models. The other reason is that the linear combinations that I love so very much, the estimate statements, the GLHT statements, and all those things, the GLM package in SPSS doesn't have to the same amount. It has less flexibility. You can get those things in their mixed package, but then all of the model output with respect to the F-tests and the R-squares goes away, and you have to do that yourself. So rather than try to kludge together multiple things to make it work, I just don't deal with it. But SPSS does do regression, and it does general linear models. So this is a correlation matrix where we have 5 predictors, not a one of which is correlated with the outcome. However, when the 5 predictors are entered into the same model, some of them are actually significant, and the overall model is significant as well. So this can happen when each predictor is unrelated or very smallly related to the other predictors. And they can have a joint contribution, even if individually it doesn't look like they would have anything to do. Another thing that you might see is what he calls null washout, which is, let's say that I have 9 predictors here, and this is their correlation with the outcome, and only one of the predictors actually has a significant bivariate correlation. When we put it in the model, the results are as we might anticipate. The first predictor has a significant slope, and none of the others do. However, even though this predictor has a significant slope, the F-test for the model is not significant. And that's because F is per slope. Remember, the F-test for the model answers the question, did you get a good deal? So how much stuff did you buy at Kohl's, but more importantly, how much did you spend? The spending, how much you spent to get your stuff, is like the number of slopes that it took to get that amount of explained variance. So the F-test for the model is evaluating the average contribution of these 9 slopes. The 8 that don't matter are downweighting the one that does. And here's another one that's probably the most interesting situation. So I have 5 predictors in this correlation matrix that are all related to the outcome. They're highly related to each other. And when you put them all in the same model, not a one of them is significant. Yet, the model itself is significant and accounts for 19% of the variance. Now, how can that be? And feel free to read from the slide.
Because they're related, so overall they have that effect.
Yeah, the common part. The common part is doing the work, but none of the individual predictors get credit. So it is entirely possible to have a model that significantly predicts an outcome, even if none of the individual unique contributions rises to the level of significance because of what they share in common. So weird stuff that can happen was the common denominator there. So this is a summary of the process here for testing one slope versus fixed slopes, and then I have an example for you. So any questions on any of that? Cool. Then I am going to call lecture 4 done. But I'm not going to shut it, because the second I shut it, I'll know I want to refer it back to something and have to reopen it again. So it's just going to sit there.
Question, sorry.
Yeah, please go ahead.
I was wondering what environments are you likely to see these kind of results, the one you just showed?
The one I just showed could happen if your predictors are very highly related to each other.
Yeah.
So what they have in common is a sizable contribution. If that common variance is related to the outcome, then that does contribute to the R-square, but none of the individual slopes would reflect that common contribution.
Okay.
And another question, is suppressing technically this similar to controlling for variables? It's related. Suppression can happen because of the common variance, and in particular in situations where predictors are negatively correlated. So your textbook has a discussion of this with residual plots that might be helpful to illustrate that concept a little bit further. But my point in telling you about suppression is just that you can't necessarily anticipate, based on bivariate relationships, what's going to happen when you put everything together. That's my point. Okay, other questions? Okay, so guess what? No more income data. It's gone. I know. I have a new data set, and it's fake, but it's based on real data. So once upon a time when I dabbled as a cognitive psychologist, I was into cognitive aging. And so a lot of the early work that I got a chance to play with data came from cognitive aging studies. And this one is based on a real study that was called the Octogenarian Twin Study of Aging. And it was data collected in like the 80s in Sweden. And they were studying same-sex twin pairs who were at least 80 years old when the study started. So from 80 to 100. So the oldest old. And they were looking at genetic versus environment contributions to change over time. And it was originally a longitudinal study. For the purposes of this, I took the data from the first occasion and I made up simulated data that looked like this. So these are fake people, because fake data are much better behaved to make an example out of, but it's based on real data. And this is from my textbook. So the readings for the next couple units here, I wrote a textbook on longitudinal analysis, but it became readily apparent to me when I first started teaching those models that if you don't understand general linear models, and in particular interaction terms, then longitudinal is going to be way harder than it needs to be. So I wrote chapter 2 of my book to talk about just regression models and regression models with interaction terms. So I would recommend reading it, because I wrote it to be readable. I wrote it for people to use in their teaching or to be able to teach themselves. It only took me 5 years of my life, so I'm kind of personally invested. And you don't even have to buy it, because the library gives it away for free. So you can actually download a PDF of the entire book for free with your University of Iowa subscription. So I'm not getting any money from pimping my book. It's just for the love of the game. So this is from that book. This set of analyses is not following chapter 2 exactly, but the ones that we'll be doing in the next unit with interaction terms will be closer. So what we're predicting is a measure of crystallized intelligence. We're calling that cognition. It is a measure that's not supposed to change over time. So it's just like a general world knowledge kind of measure. So it's a test score. We are going to be predicting that from biological age. And age is going to be centered at 85, because that was near the mean of this particular sample in this cross-sectional section of it. We're also going to be predicting cognition from grip strength, which sounds crazy, but that is the poor man's way of indicating physical function. So they're asked to squeeze a little thing, and they measure how many pounds per square inch you can squeeze, and that's supposed to indicate your physical whatever. I told you I dabbled in cognitive aging. I'm not like a real aging specialist. I'm a methodologist who helps people with aging data, is probably the more accurate way to put it. But 9 pounds per square inch is going to be near the mean for that. I have a binary version of gender, and men are going to be the reference group. And then the last variable that we're looking at as a predictor is subsequent dementia status. So as you might imagine, in a sample of adults this old, there is a relatively high prevalence of dementia of various kinds. And there were some people who never ever were diagnosed with dementia during the study. That's the majority. There were some people who were diagnosed at some point subsequent to the first occasion. And there were some people who already had a diagnosis, yet were sufficiently able to participate at the first occasion. So none, future, or current is the type of variable that I have here. And what kind of predictor variable is this, by the way? If I were to put a label on it, is this are these really numbers?
It's dummy coded, right?
It's going to be dummy coded because what kind of variable is this?
Categorical.
Categorical, yep. And a more specific version of that starts with an N.
Nominal.
Nominal. I'd call this nominal. One could argue potentially that it's ordinal because of like sort of none is good, later is, you know, less good, and now is even less good, but categorical broadly speaking. So I'm making that point because what would happen if I put this variable straight into a model coded such that 1 is none, 2 is future, and 3 is current? If I put that in as a predictor, what am I asking for? What would I get back? Do you know what I'm asking? No? Okay, let me try again. If I used this dementia diagnosis variable, so there's a column in my data set that has the 1, 2s, and 3s. If I put that in as a predictor in a general linear model, would I get a slope for it back? I would.
Yeah.
What would it mean?
I assume it'd be like per unit of age, how much, I don't know how to say it, like how much it goes up from 1, 2 to 3.
So it would be, so if we predict cognition from dementia diagnosis, the 1, 2, 3s, I would get a slope that describes the change in cognition for a unit change in diagnosis. Does that make any kind of sense? It does not. Will SAS, Stata, R, or SPSS do that for you if you ask? Absolutely. So we have to think about how to represent the variables in the model. So the fact that this is categorical is going to clue me into one of an option for dummy coding, at least one. We've learned 2 in this class so far. I'm going to go with indicator dummy coding in this case. Age, this is a quantitative variable, so I can treat it as such. These are numbers. I can talk about the change in cognition for a 1 unit change in age, which corresponds to a chronological year. What would happen if I forgot to center it? Who would we be predicting cognition for if I put in age as a predictor? What kind of person? A baby, a newborn. We would be predicting cognition. The intercept would refer to the expected cognition when age is 0, which would be a newborn. Now that's not wrong, but it's awfully weird. Likewise, grip strength is also a quantitative variable. If I don't center it, we would be predicting cognition for somebody who couldn't squeeze anything, who couldn't do the task. Now that could potentially happen, but it's unlikely that that person would have their data still be included. So what I'm going to do in this example then is go through the process of trying to figure out what the bivariate relationships are, whether or not for the quantitative variables they potentially need additional nonlinear relationships, and then put all the predictors together in the same analysis. Okay, any questions? Okay, so the code looks a little bit different than your previous examples because I'm importing data sets that are native to SAS and Stata rather than an Excel spreadsheet. So I'm still using this file save placeholder abbreviation thingy here, but I am using it in a subsequent command that you haven't yet seen, I don't think. So in SAS, the way that you tell it to import a SAS data set is by giving it a library reference, and a library is a place. So we've been working with the work library exclusively in this class up to this point. Now I am defining another one. I am calling it file save, and I am saying the place that it is right here. So I am defining a library within SAS that it can recognize SAS data sets from. So that's why right here on the set statement, I refer to the word file save. That it understands is this place. And the name of the SAS data set that I'm importing is SAS_chapter 2. It has a very weird extension to it. It's SAS7B-DAT is what SAS data sets are called. So I don't have to type that here because it understands that it's a SAS data set. But if I were to do it in other programs, I might have to. So what's happening here is I'm loading in the data set that goes on the set statement. So in this permanent directory, I'm loading in this data, but where it's going to is a different place. It's going to the work library, and it's going to be called example 4B after all of these commands have been executed to it. So why am I doing it this way? So that I don't screw up my data set is the answer. Because in SAS, data transformations happen instantaneously. So if I do some kind of coding here, let's say that I screw this up. If I run it like this, what I will do is write over the column with itself minus 85. So I'm not making a new variable here. I am destroying the old one. So if I screw this up and I run this code, the changes would happen to this data set if the name were over here, and I would have ruined the data set sitting on my hard drive. I have done that before. If there is a mistake to be made, I have made it, I can guarantee you. So to save myself from myself, I'm taking the permanent file and I'm making a copy of it, and I'm working with the copy. So then the permanent file is untouched, it stays safe and sound, and I can do whatever I need to do in the copy version that's in the work library. When I exit SAS, I don't need to save it, because all I need to save is the syntax that I wrote to make the transformations and the original version of the file. So this is like save as a new name in a new temporary place. That's what's happening here. Otherwise, you have seen all of this before, but I want to point out that the way that I've structured this is that I'm doing all the variable transformations in one step, rather than doing it in little pieces. That way, when I come back to this, I don't have to hunt through the code to get all the places where the data were changed. It's all happening in one command. So I'm making new quantitative predictors, centering them at 85 and 9. And that begs the question, how did you know to put them at 85 and 9? Well, because the first thing I actually did is run descriptive statistics to find out what reasonable centering values would be. This is the indicator dummy coding. So this version of it, I created two new variables, DemNF and DemNC, to me mean dementia, none versus future and none versus current. So when you're naming new variables, my advice to you is to use as few letters as you can to still represent what the variable means to you. Because every time, if you write a longer name, you're going to have to type it multiple times and potentially have it spelled wrong. But if it's too short, then you may not remember what it means. So I have my own naming convention systems. In this, the group that's first is going to be the reference where the 0 goes, and the group that's second is the 1. So two blank columns, then selectively recoding them into 0s and 1s. So dem group is the original categorical variable that is 1, 2, or 3. I am creating the none group as the reference by coding the new predictors at 0 for both of them. So that means the fixed intercept for the model is going to be for the none group. DemNF is going to turn on to a 1. That's going to tell me how the future group differs from the none group as the reference. Cough, cough, homework questions. The slope is always how the one group differs from the zero group. And dem NC is going to turn to a 1 to differentiate the current group from the none group. So then the model is going to give me 2 out of the 3 possible combinations. If I want to know how groups 2 and 3 differ from each other, then what will I need to do? That I've made you do in your homeworks recently to get the remaining differences. The question is, so this coding scheme is going to directly tell me how each of the alternative groups differs from the reference. The first one is going to be how future differs from none. The second one is going to be how current differs from none. What if I want to know about future versus current? Find the difference. How do I do that? I could make new groups. That's one way to do it. That's the linear combinations idea. So the estimate statements, LINCOM statements, or the GLHT statements where you have the series of zeros and ones, those things. The way that I learned how to do this, by the way, back in undergrad and grad, is to make another model with a different reference group. That works too. But it's a little bit kludgy, and it's generally speaking not helpful to have to run multiple analyses to get one thing. Then I added labels. So these get printed in the output, so it's good housekeeping, generally speaking, to label your variables. That way anybody who's looking at this knows what they mean. And then in life, you would need to worry about this. You've never needed to worry about this in your homework, though. I am subsetting the data here to just the cases that have every variable that's eventually going to be included. That way my sample size stays constant across models. There are better ways to address missing data. For that, you got to come to another class. It shows up in each of the other classes to some extent. This is what's known as list-wise deletion, where if somebody's missing anything, they get booted. There are strategies that allow you to use partial data for somebody if they are missing some things and not others. Okay. Any questions on SAS code to do this stuff? All right, Stata folks. The only thing that's different for you is this line right here. Usually refers to an import Excel command. It's just used because I have a Stata version of this data set. So .dta is the Stata extension. The way that I made this data set is to use SAS to export it to Stata. And in so doing, whoever made that routine to export to Stata understood that Stata only likes lowercase letters because it converted all the variable names to lowercase. And I looked through the options and I could not find a way around that. So in Stata, everything is going to be lowercase to match because people who wrote Stata like lowercase text. I'm doing the same thing with respect to the quantitative predictors. So new variable equals old variable minus the centering constant, and then using replace to do the dummy coding. So you've done this before in your homeworks. Adding labels, and then filtering to just complete cases as well. So nothing new with respect to that, but just another example. So Stata folks looking through here, anything look different or otherwise that you want to ask a question about? Cool. All right, R folks. I did not make an R version of the data set. Instead, I found an R package that imports SAS data. Problem solved. I had this conversation in my other class too, because there are many different ways of working with data in R, and I know that if you take classes from, say, Brandon or REL, they use something called the tidyverse. Have you heard of this? It's like its own like sub-language. It's kind of a cult within R. Honestly, like people are really serious about it. The person who helps me with my R code is Jonathan, my husband, and he hates the tidyverse. So the way that I do things is the way that he helped me figure out how to do them. If you know how to make variables or rearrange data in R using the tidyverse or anything else and you can get it to work, then your way is equally correct. The ultimate arbiter of whether your code is correct is if it does what you need it to, then it works. Then the question is, how efficient is your code? I tend to do things so that my code is transparent, but not necessarily efficient. And I also try to do things so that it looks the same across packages as well. So I am going to use a command called read Sass, which is in a package called Haven that I found. And I have to refer to the full name of the Sass data set. So here's the weird extension, Sass7bdat. I am going to make sure that it is a data frame, because sometimes when data are imported into R, it's sometimes a table, it can be a matrix, it can be something called a tibble, which I don't know what the hell that is. I think it's a tidyverse thing. But it needs to be a data frame to use it. So I don't know for a given package how it's going to come in. I always have this line here just to make sure, because it doesn't hurt to reconvert it if it's already a data frame, but I know it eventually needs to become one. Then from here, the rest of it looks pretty much the same as usual. I have my new variables being created out of my old variables for the centering, and then here is my dummy coding, where I have 2 blank variables being created and then the patterns of zeros or ones that make it so that the one group is going to be the reference. And complete cases, I don't know if I've shown you an example of this yet or not, but this is what it would look like to filter the data to just those rows that are complete with respect to all of the variables listed in this argument right here. So any questions from our folks?
For homework 5,
Yes.
will you be using a SAS data set or will you be using an Excel data set?
It'll still be Excel, and the starter syntax will help you import it just like usual.
Okay.
Yep, it's just that I wanted to start to show you like more variety of how you would get data in.
Scaffolding.
Yeah, because odds are good if you're learning a program for the first time, you don't have any data that are for that program, because like otherwise you'd already know it. And the packages differ with respect to how much they're willing to play with other people's data. So what's funny is that Stata for the longest time would only let you open like text files or Stata files. And if you wanted to import any other kind, you had to buy a separate package called stat transfer. That was how they solved the problem. It's like, well, we're not going to do that for you, but for $59.99, you can buy this other thing and solve the problem. Whereas like in SAS, it will import anything and everything and export anything and everything. So SPSS is pretty flexible that way too. Okay, other questions? Okay, so how did I know what I needed to do to the data to get it ready? So sort of a logical first step before that is descriptive statistics. So this was the very first thing that we talked about. Remember that back in the day? What's a mean? What's a variance? That's so easy now, right? This was homework 1. Make SAS, Stata, or R print descriptive statistics for you and get used to fighting with the software and the virtual desktop. So in SAS, I'm using proc means because what I'm doing right here is getting descriptive information from my quantitative variables. You can use means or univariate in SAS. I am asking it to print only 3 decimal places to clean up the output a little bit. And then I'm listing all the things that I want. So normally the default is n, mean, standard deviation, minimum, and maximum. I also wanted variance, and so I had to write out all of them because I was adding to the list. And as usual, because SAS allows multiple data sets to be open, you have to tell it which one you want to use. Then var here, not to be confused with var here. They're both blue, they're both spelled VAR, and they're not the same. This var means variance. This is an option for information to be spit out. This var means variable. Which column do you want this for? And then, of course, everything ends in a semicolon in SAS, and run makes it go. It's the analog to execute in SPSS. In Stata, the command to get descriptive information for quantitative variables, I'm using summarize. And the option, so Stata options are set off with a comma. Detail adds variance. So it adds additional information to the default short output that includes variance, which I wanted to have. And in R, I am using a package called describe, which is part of the psych package. So it does what you would think it does. So the full output for all 3 programs, of course, are in the download folder, for example 4B, so you can follow along with that if your output of choice. I've got a mix of outputs in here, I think, from usually SAS because it's the easiest to format. So this is the output for SAS with respect to those 4 variables. So my mean cognition outcome is 24.8. It has a standard deviation of 10. What does that tell me? What does standard deviation tell me?
How sparse here.
Yeah, dispersion. So 10 specifically tells me how far off on average each case is from the mean. And if I take that 10.989 and square it, I get its friend variance. And the outcome itself ranges from 0 to 44. So this number right here and this number right here are going to show up in about 10 minutes in our empty model. Because that's where the empty model starts. It's just, okay, what's a naive guess for each person? Let's give them the mean. How much variability is there to be predicted? All of it. That's where we start from. Age has a mean of nearly 85, so that's why I picked 85 as a centering point. But really, any variable that's within the range of the observed variable would be a good idea. On average, people are 3 years off the mean. Grip strength on average is close to 9, with a standard deviation of about 3 as well. And then this one, this is not technically a quantitative variable, but I'm treating it that way. So what does that number mean in the context of a 0-1 coded variable? I have more women than men. Yeah, this is a proportion. So I would say that 59% of my sample are women because they're the 1. Next up, the categorical variables, and I'm including the sex variable in that list as well as dem group. So in SAS, it's proc freq for frequencies. Note that it's table here instead of variable for reasons that are unclear to me. It's tabulate in Stata, and prop table with an embedded table in R. Gets you the proportions rather than the raw frequencies. So here is the percentage of the sample who are women, as we just learned. And then here is the percentage of the sample that falls under each of my dementia groups. So this is informative to know for a couple of reasons. I got to know how many groups I have to know how many dummy codes I need. So because I have 3 groups, I need 2 dummy codes. What happens if I had 5 groups? How many would I need?
4.
Need 4, yeah. The other thing to look at is how many people are in each category. Did I hear a question? No?
I think that was from Zoom.
Okay, it was
can
from
I ask a
Zoom?
question?
Okay, yes, I did hear something. I'm not crazy.
Can I
Who's
ask a question?
talking? There you are. Yes, go ahead.
No, I hadn't asked by the time you were asking. I hadn't said anything, so probably somebody else had mentioned it. But,
Okay, an unintended comment. Well, then
Okay.
I'll mute you so that you can mutter to yourself as much as you want. I do that all day long.
So what I'm asking is, you have centered the age at 85.
Yes.
My question is it aware of omitting those under 85? Because I thought that means 85 would lie on the y-axis, would be the intercept.
It's not going to omit anybody. It's just going to change the meaning of the model reference point to be somebody who's 85. So then the new column of age values will have some negative for the people who are under age 85 and some positive for the people who are over 85. The only way that they would be omitted is if they didn't have age, in which case we couldn't put them in the model anyway because they wouldn't be able to contribute to the estimation of the relationship for age and cognition.
Okay. So
Does
if
that-
they appear in the negative, will that be meaningful in the data?
Sure, it means they're less than 85.
Okay.
Yeah, you can use negative or positive numbers. It's up to you to set up what they mean. If we didn't center age, then we would be predicting cognition for a newborn. So these descriptive statistics inform what would be reasonable values for centering. And there's not a wrong answer. It's an interpretational preference. I could have picked 80 and said, well, I'm going to talk about the reference point as the youngest person and go from there. I could pick, 96, and then it would be the oldest person. Note that I'm not including the exact mean, but a rounded version of it, because then it's a little bit easier to talk about. If I referred to centering mean age, then I would have to dig back through the methods section of the paper to know what the mean was for that particular sample. Just saying that the reference is for an 85-year-old is immediately clear. Okay, so back to the groups then. I need to know how many groups I have to figure out how many different predictors I need to make. And I also want to make sure that I've got enough people in each of these categories to make this work. So if you have a category with only one person in it, I wouldn't keep it. It's not going to go well. Like, it's just not. It's going to cause problems. And I'm not sure how few is too few. You'll know it when you see it, though. You can get into logical combinations that are impossible, particularly when you start fitting interaction terms. The other thing that's informative about this is with respect to power. Anything involving group 3, where I only have 42 people and 7% of the study, is going to have less power relative to the other groups. So I need to know that ahead of time to think about, do I really need to ask for a hypothesis test about 2 versus 3? Yeah, I do. Because I can end up with the same size of difference, not be significant, because I have very few people with which to judge the stability. So the standard errors around each of these means are going to be a function of the number of people in that category. And so the standard error that indexes expected inconsistency, cough, cough, will be bigger if you have fewer people. Okay. Other questions so far? So I want to know, can I repeat my cough? I just laughed so hard my mask fell off. Yes, cough, cough, standard error is expected inconsistency. So standard error of anything is how far off that thing is on average in a sample relative to what it's supposed to be in the population. Specific instances would be like standard error of a intercept, for instance. So if you have an empty model, for instance, standard error of a slope. More generally, every parameter that you would estimate from data has a standard error to it. Even the variance does. They just don't show it to you in this output. All right. So before dumping everything in one model to see what predicts cognition, what I want to know first is how each predictor functions individually. Because I want to be able to say, is age not related to cognition, or is age not related to cognition anymore after you control for gender, grip strength, and so forth? Those are two different things. So I'm looking at bivariate relationships just to describe sort of what's related to what, and then we can talk about how that scenario changes when you have unique relationships instead of bivariate. So I'm combining across strategies here to do this. The quick and easy way to get a bunch of bivariate relationships at once is to ask for a correlation matrix. And this isn't something that we did much of in this class because I was assuming that you would have seen it before. But in case that is not the case, or you didn't see it in software, here's another example of that. So I am going to be asking for Pearson bivariate correlations between 4 variables, only the ones that can be considered quantitative. So cognition is going to be my outcome, age and grip strength are going to be my predictors, and I can treat binary gender as quantitative because there's only room for a 1-unit change. There's a difference between 0 and 1, and that's it. So technically speaking, I can call that quantitative. What's not in here is dementia group, because those aren't numbers. So I'm going to have a different strategy. I'm going to have to use a model to see what the bivariate effect of dementia group is on cognition, because that needs 2 slopes to be described. So by the way, this is what the output will look like in Spss. It gives you the correlations and the p-values. If you want to report a correlation matrix that's just the correlations, here's how you get that. The out command saves to the library you specify a SAS dataset that just has the correlation matrix to it. So I'm using proccore. NoSimple shuts off redundant information with the descriptive statistics. In Stata, I'm using PWCore, which stands for pairwise correlation. There is also, I think, a core or a correlate function, but that does listwise deletion. So generally speaking, you don't want to do that unless you have to. It does not give you p-values by default, and so I added them with this option, comma, sig. Can you guess what that stands for? Significance, yeah. And in R, this was a thing. So I went looking in R, okay, how do I make a correlation matrix? And it was very happy to give me a correlation matrix. It would not give me p-values. Seriously? Like, why would you want just half of the information? So I go down the Google rabbit hole, how do I get a freaking correlation matrix with p-values out of R? And found someone else who apparently solved this problem by making their own package. Of course. Yeah, that's what Jonathan always says is when I complain to him about R. Well, just make your own package.
Like you don't have enough to do.
I know. Do you know what my package would be called? I've already decided on a name. It's going to be Hater with a capital R at the end. It's going to be like for people who ate R. But no, that would be a much longer term project. I'd need like 3 years of sabbatical to be able to do that probably, and I'm not even sure I really want to. But anyway, someone else shared my indignation and solved the problem. So I'm using something called RCore that this person who made the HMISC package, which stands for miscellaneous, I think, and I got it to work. The only catch is that the person who wrote this package was insisted that your data be a matrix, not a data frame. Okay, so there's a function I used here, as matrix, to trick it. So now it gives me a correlation matrix the same as this and a separate table of p-values. So it's 2 tables, but at least you get the p-values. So that's in your output file. And I have type equals Pearson because there are other kinds. So you may have heard of a Spearman correlation. Does that ring a bell? That's when you rank order your data first and then do a correlation on it. It's used for like extreme observations, like to give them like less influence on the solution. There's all kinds of different correlations though, which is why when you're reporting this, you want to say which kind it is, and it's Pearson. Okay, so any questions on the code to generate correlation matrix? All right, so a little review about the idea of correlation then. Review / perhaps new information. So on the diagonal are 1s, because that's how correlated each variable is with itself. So that's not helpful. The bottom triangle under the 1s is the exact same information as the upper triangle, just transposed. So in practice, you would only need to give the bottom or the top and not both. I tend to go this way when I look at these things. So here is the Pearson correlation between age and cognition. It's negative. The p-value for it is below hand, so it's significant at an alpha of 0.05. What does this mean?
The 1?
Yeah, this number right here. What's that mean?
Like what their correlation is?
Yeah, like put it in a sentence.
Oh. If I don't know, cognition goes down 17, I don't know if it's a percent, 17-ish each unit of age.
Think of these as standard deviations.
I don't know them.
You're very close though.
Okay.
Yeah, do you want to try, Chris?
The
Or-
younger, you'll have higher cognition.
Yeah. Younger people are smarter. That's what this means. And by younger, I mean under 85.
Youths.
So for every standard deviation increase in age, cognition goes down 0.17 of a standard deviation. So is this a big relationship?
No.
Not really. It's significant though, because I have 550 people. So this would be considered like a small-ish effect size There's labels that go with these things. Those are less useful to me than looking at the number. What's the best this could be? Yeah, -1 in this case, right? -1 and 1 are both equally strong. They just indicate as x goes up, y goes up or down. So this tells me that age is related to cognition. It's negatively related. I don't know how much of that is because of other things that age is correlated with, such as strength or frailty is really what they're talking about in this population. So what's this correlation tell me? This is grip strength in pounds and cognition. Yep, stronger people are smarter. So go hit the gym. It'll help your grades or something. Yes. Or go study. It will make you more powerful. Either way. These are associations, my point is. I'm poking fun at the idea that these are observational data. We cannot make causal inferences about any of this. But there is an association such that people who can squeeze more pounds did better on this test. Why that is, I have no idea. But that's not for us to figure out. And this is a positive relation, but it's also not very big. Now, how about age and grip strength? Correlation between the predictors. What's that tell us?
Younger people are stronger.
Yeah, younger people are stronger. We already knew that. Now, not like lockstep, though. This is still not that strong of a relationship. But this also tells me that when I try to put age and grip strength together as predictors, their relationship is going to be different than this because they share something in common. Now, I don't know how much of what they have in common is also related to cognition, but if they have something in common at all, then that's a logical precursor to their unique effects being different than their bivariate effects. How about the correlation between cognition and gender?
If it's negative, then that's closer to 0, right? So there, I think it said that the men have the stronger cognition.
Yeah, to answer that question, you have to know who's the 1 and who's the 0. So what the correlation means is that as x goes up, y goes down. As x goes up in a binary variable means as you move from men to women. So yeah, as you go from men to women, cognition goes lower. So yeah, the men are doing better. Significantly so. How about grip strength and gender? Men are stronger. Okay. Particularly with grip strength. That's why I don't open my own pickle jars, right? Actually, the best swag that I ever saw for a cognitive aging study was Susan Kemper, if you're listening, from KU. She's retired now. But she gave out, those rubber things that you use to open jars?
Uh-huh.
That's what she gave out as swag for the older adults who did her studies,
There you go.
with her logo on it. We still have one in our kitchen. That's what I use to open jars. So I'm like, I don't need another coffee mug with a research study logo on it. I need a jar opener.
Yeah.
So that was very, very smart of her. So,
And-
yeah, question?
Lisa, I don't want to speak to the men, but a trick is if you tap on the jar,
Yeah.
the air goes, and you can easily open it if you tap on the jar.
Okay, that's good to know.
Us science people can vouch for that. There's science behind it.
There's science? Okay, good. Well, then there's also the strategy of, I'm too weak to do this. Can you just do it for me? I'm not afraid to play that card every now and again. Like, can you go get the 50-pound bag of water softener salt out of my car, please, and carry it downstairs for me? Thanks. Sorry, I'm a girl. I don't want to, is what that means. But anywho, gender and grip strength are related. So what that means to us, besides speculating about the reasons for that, is that if I put them together in the same model, their associations with cognition are potentially going to be different because they have this thing that's in common. So this sort of overall picture of how your variables fit together is a really important first step. If you found that two predictors were correlated nearly perfectly, then you probably can't put them in the same model and have a decent shot at looking at their unique contributions, or you screwed up your data. So that's another possibility. So for instance, going back up to the code here, if I did a copy-paste error and I did something like this, then I'm going to get a perfect correlation between age and grip strength because they were both made from age. So seeing that perfect correlation should clue me into, like, I need to go check my code because that's not supposed to happen. So what else doesn't this table tell us then? In addition to unique information, what kind of association am I assuming between all of these variables? There's a word for it and it starts with an L. Linear. Do you think it's possible that there's diminishing returns? Like the effective age sort of wears off at some point or accelerates? There's a phenomenon in aging called terminal decline, which is exactly what it sounds like. It's a cliff that you sort of fall off at some point as your health goes downhill. So it's possible that there's nonlinear associations in this. Do I have any information about this from this table? Nope, I need a model. So I also want to check to make sure that just assuming that age is linearly related to cognition and grip strength is linearly related to cognition is a reasonable thing. So we're going to look at models for that. And then the variable that's missing is dementia group. I can't put that in the table. Now, what might happen if I tried to put the dummy codes I made in the table? Would the programs let me?
I don't know, because there's 3.
Well, if I put in the variables that I made, where are they? These ones, like the dem NF and the dem NC.
Then
The-
yes.
Yeah, it'll let me. This is a recurring theme throughout that. The answer to that question is yes, the program will let you do stupid things. And it doesn't matter if it's a Windows-based program like SPSS or if it's hard-coded in R, the program will let you do stupid things. And that is why I have a job. So what if I tried to do that? I put dem NC and dem NF in there. That's better, right? Because it's just 0 or 1, just like gender is. Let's go back to what they mean. It's easier to see it in the SAS code when they're next to each other like that. So dem NF, I told you, is going to eventually tell me how the future group differs from the none group. But if I just have this column right here, that is not what it means. This variable, if it were used separately, all by itself, tells me how the none and current groups put together, both coded 0, differ from the one group. And this variable would lump together none and future and tell me how it differs from current. They only hold the group-specific interpretation when they're put together in the same analysis because then we have unique effects that go along with that. So I could put these dummy codes in the correlation matrix. It would not tell me what I think it does. Okay. Questions? All right, so let's do some modeling. Cognition, empty model. You guys are very good at this by now. You will get even more practice in homework 5. Do I technically need to do this? In real life, no. For pedagogical purposes, I feel like it's useful because this is what R square is going to be relative to, is this result. By how much did your residual variance go down requires you to know how much there was in the first place. So we've got my empty model for cognition in each of the packages here. And lo and behold, the mean square error or mean square residual that gives me my residual variance is 120, just like the variance of cognition was when I asked for it descriptively. and the mean of the variable of 24.82 shows up as my intercept. So it's recreating the univariate descriptive statistics for mean as central tendency and dispersion as variance. So let's check out then the quantitative predictors. I've got a model now that has linear and quadratic age. I knew from my Pearson correlation matrix that I at least need this much, that there is a linear relationship between age and cognition. I don't know if there needs to be a nonlinear relationship. Quadratic is a quick and easy way to check. There are many others. So I have this highlighted here to remind us that it's both linear and quadratic together that create a quadratic pattern. If you just put in age squared, it does not mean quadratic. It would have to do the job of both variables. So this is something you've seen before. You had to predict golf scores from a quadratic function of enthusiasm a couple homeworks ago. So I've got age 85 and then the squared version as two separate predictors. In Stata, it's hashtag old, age 85, and in R, there's multiple ways to do it. Here's a shortcut way that doesn't require making a new variable. This I function thing where you're allowed to square it inside the parentheses. So here are my results. I have a significant model, hooray. My two slopes work together. They get an R square of 0.03, not super impressive. What I really want to know though is this term right here, because that's the thing that sets it apart from just a regular old linear relationship. So I have an estimate of 0.0175. Its standard error for expected inconsistency of that slope is 0.03. Estimate divided by standard error gives me t. That's how many standard errors away from the null hypothesis I am, and then here's my p-value. So what's my story here? Do I need age squared?
I don't think so.
I don't think so either. So that p-value tells you, cough, cough, homework question, the probability of finding a slope that big if the null hypothesis were true. So if there is no quadratic age slope in the population, I would get one this big like 58% of the time. In other words, it's well within expected sampling fluctuation of inconsistency around 0. So no, it doesn't look like I need it. So here's a question then related to that. The R that I got out of the correlation matrix, if I square it, is 0.0291. The R square that I got out of this model is 0.0959. Just a bit higher. Do I know from this result if that change in R square is significant? What do you think? We got votes for no, it's not significant, or I don't know.
I don't think it's significant, but I don't know why. Like, I don't know which number I should be looking for.
Okay, let me put it to you this way.
No p-value.
This much is the Pearson correlation. If I computed a standardized slope for that unstandardized age slope, that would be the same estimate as the R I got out of my correlation matrix. So the term that separates the R square that goes with the correlation from the R square that goes with the model is just this right here. So there's three potential values of interest here. I've got what is the R square from before, which is 0.0291. What is it now? And how do they differ? This F-test for the model judges the now R square against 0. So this 0.02959 is greater than 0. In order to know whether it is more than what it was before, I would need a test of what makes them different. And in this case, the only thing that makes them different is this additional slope right here. So if this additional slope is not significant, then the increment to the r-square it created is also not significant. One-to-one correspondence when there's only one slope being added. So this is the tricky part, because you might look at this f value for the r-square and be like, well, that's significant. This one is. What it is now is significant. But what I'm asking about is relative to what it was in a linear-only model. The increment to the r-square, the change in the r-square, is not significant if the thing that caused the change is not significant.
So if you wrote this up and somebody said to you, why would you have used linear? Quadratic makes more sense with age. Then you would say, not really, because this.
I would say, thank you for that helpful comment. Based on that suggestion, we reanalyzed the data to examine the possibility of a quadratic age slope. We found that it was non-significant, and I would also want to report the effect size. It accounted for, 0.0000 more % of the variance. Based on these results, we decided not to keep quadratic age. And that's now reported on a footnote in page 12. Yep. Okay, other questions? Same story with grip strength. It could have a nonlinear relationship. Let's see if it does. Survey says, which by the way is a game show reference. I have to explain this to people now, that's how old I am. The Family Feud. Richard Dawson used to point at the board and say, survey says, and then they would reveal the answer. So, I am Richard Dawson. Who is it now?
I don't know.
Is it Steve Harvey?
Really?
Yeah, it's still going. I know that.
Yeah.
So survey says, do we need quadratic grip strength as a predictor? Doesn't look like it. Same story. So it increased the r-square a tiny bit. In terms of practicing what to do with quadratics, though, there are only 4 possible patterns created by a quadratic slope. It takes the linear slope at where the predictor is 0, and it makes it more positive, less positive, more negative, or less negative. So which is this? We got a positive effect of grip strength at 9 pounds. What happens to it as you get further up on grip? It's more positive. And the rule is, to interpret it correctly, what do we need to do to it? Double it. Multiply by 2. Cough, cough, homework question. Yeah, because the quadratic itself is half the rate of acceleration or deceleration. So you got to multiply it by 2 to get to the full rate. So the way I would put that into a sentence is that this is the slope per pound of grip strength at 9 pounds specifically. So we're talking about the slope that is tangent to the curve at that point. It becomes more positive by 0.032 per pound. So next week we get to start interaction terms, and the exact same logic is going to apply without the 2. Interaction terms take their constituent main effects and make them more positive, less positive, more negative, or less negative, and you just got to figure out which of the 4 you're looking at. How about the other one? Which pattern is this? I have a negative slope of age at 85. What happens to it as age increases? Less negative. Yep, slows down. Eventually becomes more positive, which is why I worded the answers to your homework that way. Yep, it becomes less negative by 0.017 times 2. Yes, indeed. So it looks like in both of these cases that just having a linear slope for age and grip strength in relating to cognition is going to be sufficient. So we can call those good. How about for gender? Do I need to test a quadratic slope for gender? Nope. There's only one possibility. There's only a difference between 0 and 1, so it can't be nonlinear. You'll probably get dots if you try, where that term would be in. I do have to do it for a dementia group, but that's going to have to wait until garbage day. All right, questions as we wrap up?
So formative due on Monday.
Formative due on Monday, and I'll,
Next test, our next homework is due the following Wednesday.
correct.
Okay.
Yeah, like 2 weeks from yesterday.
Yeah.
And I will let you know as soon as it is available.
Cool.
Yep. All right, then we will call it a day. Office hours start at 3:30. Let me know if you need anything. Have good weekends.
Thank you.
Stay warm.
Yeah, you too.
Yeah. Yeah, so over this weather.
I know.
Is it spring or winter? I don't know.
I should be in shorts by now. That's what I know. I should not be in a winter coat and gloves going
I
into
know.
work.
Like, I don't remember anything.
The other day I wasn't wearing a coat at all, and I'm like, oh, wow, now I'm back. Gross.
Exactly.
Yeah. I don't. Yeah, I don't really think it's